Yeah, that's what. Will you be able to make it?
Uh, that will be on this platform or
Yeah, on
which
this
platform?
platform.
Okay. Okay.
Yeah, on this platform. So just keep an eye out at the inbox. I'll be updating us over there, so we know how it's going. I'm trying. Okay, so I'm going to share my screen for the new notebook. Yeah, this is on the norms and the distance. I think this one refresh in your mind, so I'm not going to do a lot of explanations over here. Just do more of the codes. Let me. Okay, please give me a minute. Okay. So yeah, so remember everything about the norms and the norms and distances. Um, Copy this. Okay, right. So the norm of a vector is just the length of a vector, right? Um, Length or magnitude. You could call it magnitude too. So it's just how long it is from the origin, which is zero. All right, and in ML we use the norms to measure the distance between two different data points. You can also use to normalize the features to control the model weight. Usually, the depending on your number of features, your model can become very large. So using normalizations, you could shrink them and still retain important features, right? Using norms and Euclidean distances, right? So there are different kinds of distances, and and we're going to start with the Euclidean norms, right? That's the L2 norm, and that's the most familiar one. It corresponds to the standard geometric length of a vector, and let me bring a formula. Okay. So this is how it's defined, right? I'm sure you've seen this one a lot. This is the magnitude, usually called the magnitude of a vector, and it's just the square root of the components. Sorry, the sum, the square root of the sum of the squares of its components. So you square all the components of the vectors, and then you find the square root of that, and that's essentially the Pythagorean theorem generalized for higher dimensions. So it just represents the shortest straight line distance from the origin to the point represented by the vector, right? And that's how the that's what the Euclidean norm means in general. So let's code over here. So consider we have a vector v, which is 3, 4. I'm going to use NumPy for my programming so that I don't spend a lot of time. But when I share it, I'll share the notebook with you. I'll have the Python the Python lines and the NumPy line, so you can just compare both of them and see how it works. Okay, so say vector 3 4, right? Let me create. So vector v is a NumPy array, which is so as for this part, because I'm typing, you can also be typing with me and see how it will run on your notebook and use different values to get different answers and all of that. So this part will be where from here it will be a bit slow, just so you can follow and catch. Okay. All right. So NumPy, we already know how to create the vectors represented with NumPy arrays. So this is what I'm doing over here, and I'm going to create the L2 normalization or Euclidean norm. I'll call it Euclidean norm, right? You can call it anything depending on what you do. So this is a linear algebra function in NumPy. Once I call that, it's going to do all the calculation for me. I think I have to do the math side so you understand, you see what I mean. But yeah, so once I call this, everything is simple. I don't have to stress to do the square of like writing this in Python code, but I'll do that too so that we see how it looks like. Okay. All right. So once I do this, I say I call this function in NumPy and I pass my my vector in, is going to automatically calculate the Euclidean norm for me. Okay, so let me just call Euclidean norm. Sorry, Euclidean norm and run. Use the print Euclidean norm. Says what NumPy has no. I think the spelling is linear alg dot norm. Okay. So yeah, so this is just 3 squared plus 4 squared, all square roots. So 9 plus 16, that's 25, and root of that is 5. So using NumPy, easy peasy, you won't feel the stress, right? So let's just do this in Python as well. Okay. So let me start by creating a function. All right. So I'm going to create a function, and creating a function, you use the def. This you call this def create a function. I'm going to do it differently so that we can tell the difference, right? So this is my function L2 norm, and the arguments that I'll need is just maybe I'll use a as a different vector. So my vector will be a, or anything, it could be anything, right? And then you close it over here, and once you hit enter in Kaggle, it will do the indentation for you. So I'm trying to find the sum, right? I'm trying to find a sum. I'm trying to do some math, right? In that, I'm trying to do some math. So because it's not just one calculation I'm doing, like I'm trying to, it's not just, I'm not just taking square roots, right? I'm doing square roots, and the result of that square root of that squares, I'm going to also do something with that. So first off, let me create something to store my values. Sorry. So total, I'll explain this. So this is just empty for now. I'm going to store something in there. So it should go through whatever vector I give. So for the values in A, which is the vector or the arguments that will be passed in my function, I'm going to close that. I want it to I want it to I want it to square all the values, right? So I want it to square all the values, right? So doing double asterisk is square. If it's one, it's multiply. If it's two, it's square. Okay. And if this is like two is exponent. So if I change this, It's just going to be exponential value. So this is exponent 4, exponent 3, exponent 2. Okay. So I want it to add. I want to store and add. So right. So I'm going to do add it. Like once do the exponent, I want to add it and store it in my total function. Okay. Right now it's 0. But as I pass, once I give it the value, once I pass in my argument, which is the vector, I want you to square all the elements in the vector. That's the x in A, and then do it, and then store it in my total, and after that, return. So the final value should be should be square root, right? And square root is essentially that value exponent half, right? Exponent 0.5, right? If the square root of 25 is just 25 exponent 0.5, and then yeah, so that's what I'm trying to do over here. So this is the function, and once this is done, that's also work. So all I have to do is to call my function. So let's create another vector. So my vector A should be, let's say, 4 and 5. I want to get different answers so we can, so it should be square brackets, right? Because I'm creating a list. And then print my function. So L2 norm A. Right. And let's see what happens over here. It's not running. Let me run everything again. Guys, let me refresh my page. Give me a few minutes, 1 minute to refresh the page. But I hope the explanation makes sense. This is just one way to do it, but there are other ways too. So I'm running everything again. Yeah. So you can see done the calculation. Let me use the same value so we can compare there. Right. So once I change this over here, I should get 5 too. Right. So created a function that's essentially doing what this is doing. And that's the beauty of the libraries. With the libraries, it has already created a function for you. So all you need to do is to call it and run it, and then you are good to go. But if you want to work with other functions, you have to create it yourself. So I created my function and I called it over here, pass my value in it, and then I get I get what I want. So this is how to calculate the Euclidean norm. Another There's another way to do it. Once I share the notebook with you, you see there's another way to do it with a library called math. That one you can just use the you call square. You can type the math functions like square root, square. You can type it. There's a way to type it. So square root is just SQRT. Okay, like stuff like that. And you can also do that and get your to calculate your Euclidean norm. Okay. Do you guys want to try your hands on it? Yeah. Let's try our hands on it. Let me give you a 3D norm and run it and see what happens. Okay. Okay. So I want you to find the Euclidean norm for this in pure Python and print the result. So you can just use this one. You can type this, and when you get to where you have to implement the Euclidean norm, you just have to change this from 2 to 3. and then run it. Let's see and you see the results. Okay, we have like 2 minutes to do that. Hello, Daniel. Will you be able to do that?
Yes, please. I'm coming.
Okay, okay, all right.
Um,
Let me know when. Let me know when you finish.
yeah. Hello. Hello.
Yeah, you can share
Hello.
your screen.
Please,
Let me
please.
see.
Yes, I've created it. I'm running my code, but it seems that the things is loading, but it's not stopping. I don't know why.
I'm going to make you presenter. So you share your screen. You share your screen with me. Okay.
Okay.
Okay. All right. So you can share your screen.
Mm, okay. Yes, can you see?
It's loading. It's loading. Yes, I can see. Okay.
It's loading, but it's not stopping. The same thing as this one. I've been trying, but I don't know what's the
You
problem.
you
But the other page are working.
you can refresh. You can refresh the page, like refresh the site, and then run it in like that. I think I also getting that alert when I was doing this. And once it finish loading, just hit run or
Oh, okay. I got 7.
okay. Okay. You can do run or so that it runs everything for you again.
Okay. Okay.
Invalid decimal virtual.
Oh no, it's the previous one. I've not
Okay, okay,
completed
okay.
the one.
Yeah. All
It's
right.
this one I got 7.
Okay. That's fine. That's nice.
So, yeah.
Sorry.
Please,
What?
you were. Hello.
Yeah.
Hello.
Hello. I'm listening
Yes,
to
please.
you. Yeah.
You were able. Yes, on your. I don't. Can you see my screen?
No, I know. Please share again.
Okay.
Share it again. Sorry.
Okay, please. I was. I see that you were able to put 1 2 underscore none, but I wasn't able to do that. I don't know what is the problem.
It's L2, not one. Sorry. L2 underscore none.
Okay.
Yes.
Oh, okay. Okay.
L2.
Okay. Thank you.
Yes, yes.
Okay.
Okay. Thank you very much. All right. So the next one is the Manhattan norm. Right. The Manhattan norm is also instead of squaring the components, it sort of sums up the absolute values. So you only travel along the grid lines, like instead of diagonally. Instead of like as a diagram, you'll be moving along the lines, right? And I think it's a visualization. So okay, there is this in the notebook. Let me share that instead. Let me share that. All right. Mine is also loading. Let me I have to refresh my page and run everything again. Give me a second. Yeah. Still, I was trying to visualize the what I mean by the distances and what it means and all of that. But it keeps loading, but it doesn't work. Okay, so if you can see, this is the Euclidean distance. This is also different ways to calculate it, right? Where you can just do the subtraction and do the square. That's for two different distances for two different points. So what we did was just for one point with respect to the origin, right? And this is for two different points. You have point A, point B. It's basically the same thing, but then instead of just A to the square of two, you what you do is you do the subtraction over here and do the square of two. And the I here just indicates that it should go through it should loop through the whole vector, right? So that no matter the length of the vector, it's going to do the subtraction element twice. So I'll share this with you so you can check it out and see what's going on. Okay. Hope this makes sense. So this is with the math and this is with NumPy and same thing. Once you call the function and then you do the math over here and then that's all. You want to find the distance between this and this. You just subtract and then that's all. Okay. So this is a visualization to understand what I was trying to say. Right. So point A and point B, the Euclidean distance is this distance is the Euclidean distance. Okay. The distance are the diagonals or the hypotenuse. And the Manhattan distance is the distance along the grids. So this in the x direction and this in the y direction. That's that, that's the Manhattan distance. Okay. And also this is the calculate, this is the equation that I was saying. It's just the absolute, the subtract, you subtract the absolute values and sum them up. So given, let's do for, so we need 2 points for that, right? So that's the L1 norm. Euclidean distance the L2, the L2 norm, and Manhattan distance the L1 norm. And this is the formula for that. And that's exactly what's going on over here. We have distance. You want to find the Manhattan distance of points A and B. Okay, using the same explanation I used with creating your own function. So you do that and you create something to store your values. So for you create a loop that should go through your vector A or whatever vector you pass through. So vector A, for that range of vector A, you want to find you want to find the absolute value of the subtractions. So you subtract A from B and find the absolute value and sum it up. That's what this is doing. So I want to sum the absolute values of this up and then return the total. And once you do that, that's how it works. So that's for writing the Python code yourself, right? Do you want to type this? Do you want to type it out and see how to work?
Uh, but because of time, since we will share the slide with us,
Yeah, yeah.
I think I'll do that later.
Okay, okay, okay. All right. So, and this is also doing the same thing with NumPy. Because there is no definite like the previous one, you just call the linear algebra norm, and then you can do the Euclidean normalization. With the Manhattan distance, you have to sort of do it manually in a way. So this is my two vectors A and B, and I want it to return the sum of the absolute values of A minus B. Okay, and it's almost the same as this, just that instead of using the symbols and the logic, you are just using words over here, or you're just using the functions. Okay, and you still get the same value. All right. So I don't know if you already know Python, you understand what's going on with the plots over here. But then if you don't stress. Just the main thing is just specializing it for you to understand what it looks like. Okay. So you can also try these exercises with a 3D, with a 3Ds, calculate the norm in 3D and also the Euclidean distance of 2 points. Okay. Yeah. So next one is the inner products or the inner products or dot products. Come. All right. So vector addition, subtraction, and scalar multiplication will change the vector's position or scale, and the dots product is also known as the scalar product or the inner product, and it just provides a way to multiply two vectors that will yield into a single scalar number. And this scalar number tells us the relationship between the directions of the two vectors and makes it important to measure them for measuring the similarity and understanding some of the geometric relationships in the vector spaces. So yeah, so that's what, so it just measures how two vectors align, how similar their directions are. So if the value that you get, if the inner product is a large positive, it means that the vectors are pointing in similar directions. And if it's zero, it means they are orthogonal. That's perpendicular. And if it's negative, it means they are in opposite directions. Okay. And vectors the vectors that you pass through must have the same dimension, in the sense that if you are using 2D vectors, it should be both of them should be 2D. If you are using 3D, both of them should be 3D. If you use different dimensions like 2 minus 3D or 2D times 3D, you won't be able to apply this to it. You won't be able to do it. Right. So for two vectors A and B, or V and W in this case, in whatever vector space that you find yourselves in, their dot product is simply denoted as A dot B, right? And it's calculated by multiplying the corresponding elements and summing the results. Okay, so you just multiply. So for this vector V and W, the dot product is just V times W plus V2 times W2. And the value, you get a single value, and that value will be the dot product, right? And it's a simple. The zip is, let me use the, let's use this to explain, right? So dot products of V and W. First of all, we will check to see that the length are the same. You can skip this if you know you are going to pass the right length, but just here in case, just to explain, right? If the length of V and W are not equal, you're going to get an error that will tell you that the vectors must have the same dimension. But then you could remove that if you're writing a function. And just like we did, you set a variable that will store your total, and then loop through your vector. So I want you to loop through the vector, and what I want you to do is to sum the. I want you to add it and sum them up, right? So sum the products of V and W as element wise as you go through, and it's almost like the same thing. Once you able to understand how to write the functions, and you know what like the equation is, it's easier to reproduce the function you're doing. So I know that I want to find V times W and sum them up and to my dot product. So that's the same thing that all we just changed here was the math, was the calculation that's going on over here. Okay. So once you do that, you just call your function and pass in the two vectors V and W, and you're going to get your result over here. This is one way, and you can also use NumPy. This is NumPy on a 3D on the 3D vector. So that one, there's a function that you can just do. You just call dots, np dots, and you do your multiplication. So this function, so that's this library or this function here. So you can still go and check the documentation of the np dots function. It's basically doing something like this. Okay, basically doing something like this. It's going to take your value, multiply it, and sum them up and return a result and give you an output. So once you call it, it eliminates the need to do all of that addition and multiplication, and then you can just pass in your vectors and get your output. So that's what makes the NumPy easier to work with. And yeah, so this is the difference. And once you do that, you get your results over here. So right, this is just, yeah. And if you have a vector, the dot product of the vector with itself is going to give you the, so this is the dot product of the vector with itself, right? If you take without the square roots, it looks like, if you take the Euclidean norm without the square root, it's almost like it's just like the dot product, right? So if you the dot product of a vector with itself is the same as the square of its Euclidean norm, not the norm itself. So once you square this, you're going to cancel out the roots. So you realize that this is equal to this. The dot product of a vector with itself is the same as squaring the Euclidean norm. Alright. Yeah. That's just by the way. So this the next thing is the inner product axioms. Axioms, as I explained in the previous one, are just rules. Axiom just means rules, right? Or yeah, rules. So for a vector to be so let V be a vector space of R, right? The inner product has to satisfy these four main axioms or these four main rules or properties. The first one is the symmetry, meaning that the vectors. What's going on? Did I cut off? Can you hear me? Hello. Can you hear me? Did I get cut off, or it was just now?
No, please, can you said the axioms? Hello.
Yeah, yeah. Okay. So okay. So I was
Yes,
I was in the
please.
axiom. Okay. All right.
Yes.
I just got a notification that it got disconnected. That's why. All right. Thank you. Let me go back to sharing my screen. So was I sharing my screen this whole time?
Yes.
Okay. Okay. Nice. Coming. Okay. All right. Yeah. So the first one is the symmetry. Then it just means that the order of the vectors does not matter. So if you swap them, it shouldn't change the results. Almost like the commutative property. Right. So the way it just means that u times v or the dot product of uv should be the same as the dot product of vu. Right. Just like commutative property. And the way to test it is just by just how do I say it? By just swapping them. Okay. So I create my vector u and vector v, create a function that just does the dot product thing. Alright. So I think because I had already created it here, just call the function here and that's it, right? So dot product of this is just going to return the sum of this times this, right? So this is another way to using write the dot product function without going through all this, without writing it as a function like this, without doing all these lines. You can write it like in its literal sense, the sum of this times this in the range of the values. So take the range of this, take the length, go through element wise and multiply them, and then return the sum of that. So this double equal to sign just returns a boolean value. Boolean is true or false. So once I have this, my output is going to be either true or false. Okay. So just testing if the symmetry holds. And then we can just also print them separately. So I can just so I can see the results. I can do print LHS and print right hand side as well. And let's see. So the output should be equal. Whatever this gives me should be the same as whatever this gives me. And what is going on is I said and compare this and tell me if it's true or not. And that's what I did. I don't know. I think anytime it keeps loading and it's not coming, I have to refresh again. And I don't do that because of time. But then yeah, when I share the notebook, you see when you run it, you get it. Okay. And the same thing in NumPy, just .uv compare .vu. It's simple by all you need is just call the dots and the NumPy, and then your output will come true. All right. So if it doesn't match, it will be false. Yeah. There will be an exercise on that, so you can also test it and understand. But then as you go, you realize that it's so similar, and it makes the explanation easier because we are sort of repeating what we are doing. The only thing is knowing what function to do, what function to use. And the only way to get that is by reading about the documentation, reading about the how the NumPy library works. You could just go online and say how to do maybe dot products with NumPy, the function for it will come up. Or you could go and look for the NumPy documentation and take your time and read through. You find so many useful stuff in there. So the second one is the linearity. So the first one was symmetry. Second one is the linearity in the first argument, which essentially means that the scalars in addition can be distributed inside the first argument, and the inner product is linear in the first vector. Give me a minute to linearity in the first argument. Come on. Oh, my internet disconnected. Shit. My phone went off. My phone went off. That's why. Okay. All right. So let's go on. So so this is also one of the axioms of the in dot products, the linearity in the first argument. So if we have our vectors u, v, and w, and our scalars a and b, or constants a and b. Once we multiply, or we find the dot product of au plus dot product of bv and w, it should be equal to us finding the scalar of uw the plus the scalar of b and w. Okay, and that's what we are also doing in the code. So first, you see, this is in normal code because we've already written a function of the dot products. Just call it over here and work with it. All right. Yeah. Okay. So as I was saying, first for two vectors like u and v, we already know they are dot products, right? And the linearity in the first argument is basically saying that the dot products will distribute over vector addition and scalar multiplication in the first vector. And if we add two vectors in the first slot, the result is the sum of their dot products. And if you multiply the first vector by a scalar, the dot product will scale by that same amount. So think of it like v is a direction of light, and the dot product u of v is the length of the shadow that is cast, right? So if you add two vectors, such as u1 and u2, the shadows will add up. And if you stretch one vector by a factor of c, the shadow will only become that will become the the factor that you stretch it by, it will become longer by c. It will be c times longer, and that's exactly what the linear um, property means. So our left hand side is c u plus bv, right? And our right hand side is the dots a times the dot product of u w plus b times the dot product of v w. So a times the dot product of u w plus b times the dot product of v w, and they have to agree to the linearity the linearity property, which says that the left hand side minus the right hand side should be less than that. Right.
Hello.
Yeah, hello.
Hello. Yeah, please, why did they write it should be less than 1 to the power negative 9?
That's how do I even explain it? It's just like um there is because of one. Sometimes I'm trying to find a way to explain it with the equations that we used. Okay. Hello.